Hi, Mr. Richards here. Today's lesson is on representing relationships. Our goal is to translate tables and graphs into linear equations. Let's start with our real-world link. To achieve orbit, the space shuttle must travel at a rate of about 5 miles per second. The table shows the total distance d that the craft covers in a certain periods of time t. Write an algebraic expression for the distance in miles for any number of seconds t. Well, as we look at between our time and our distance, it looks like, well, we're increasing by 5 as we go down. So try 1 times 5, well, that's 5. 2 times 5 is 10. 3 times 5 is 15. 4 times 5 is 20, and 5 times 5 is 25. So we could write this expression simply as 5t. And to describe this relationship in words, we can say the distance is 5 times the number of seconds. And graph the ordered pairs and describe the shape of the graph. Well, on our x-axis, let's put our time. And that's going to be in seconds. And on our y-axis, we're going to put our distance. And that's going to be here in miles, or mi. So our first point we have is 1, 5. 1 second, 5 miles. So we have 1 second and 5 miles, and that meets right there. And then we have 210. So we're going to have 2 and up to 10. So that's going to be there. Then we have 315. So 3 and 15, and that intersection is there. So 315. Then we have 420. And 525. And when we go to describe the shape of this graph appears to be a line. So we can write this, the shape of the graph appears to form a line. So the graph is linear. Let's continue on into our examples. The total cost of tickets to the school play is shown in the table. Our first question is asking us to write an equation to find the total cost of any number of tickets. Describe the relationship in words. Well, we have our tickets T and our cost C. Let's look for what is increasing here in our cost. Well, to get from $4.50 to $9, I am adding $4.50, since $4.50 plus $4.50 is $9. From $9 to $13.50, I'm still adding $4.50, and I'm adding $4.50 again. So when I go to write my equation, let's look at our variables first. We have our cost, which we can say is going to be our C. And we have our tickets, which has been established as T. And so we're looking to find the cost. So C is going to equal, well, what are we paying per ticket but $4.50? And when we look to put an operation there, it's going to be multiplication. So our cost equals $4.50 times T, since each ticket costs $4.50. Now use the equation to find the cost of 15 tickets. Well, we're going to have T to equaling 15 here. So we can use the equation C equals $4.50 times t. We can substitute in the 15 for our tickets, and that's going to be multiplication. And $4.50 times 15 is $67.50. So our answer there is $67.50 for the 15 tickets. So we can look at our table, look for our increase, create an equation, and then use that equation to find the cost of any number of tickets. It's really pretty neat. Now we can go from a table and coming up with an equation and a solution, and now we can use a graph to do the same thing. Write an equation to find the total number of trees y that can be saved for any number of tons of paper t. Well, our first step here is going to be to find the rate of change, otherwise known as the slope of the line. And there's our slope formula, m equals y2 minus y1 over x2 minus x1. That's our definition of slope. Now we need to pick 2 points from that graph. Well, let's keep it simple. Let's pick our 117 as one of the points and 234 as the other. Let's call the first ordered pair our x1, y1, our second ordered pair our x2, y2. Now we can make our substitution in. So m is going to equal our y2 was 34, our y1 was 17, our x2 was 2, and our x1 was 1. Well, as we simplify this now, 34 minus 17 is 17, 2 minus 1 is 1, and 17 over 1 simply simplifies to 17. So our slope of the line, or our rate of change, is 17. Now to find the y-intercept for our equation, use the slope and the coordinates of any of the points to write the equation of the line in slope-intercept form. So we need to come up with an ordered pair, and let's use that 117 again. So when I go to make my substitutions in, my x is going to equal 1, my y is going to equal 17, and my slope, my m, we just calculated above at 17. So when I have y equals mx plus b, I know my y is 17. I know my x is 17. And I know my slope is 17, and I know my x is 1. I'm looking for the b. So 17 is going to equal 17 plus b. If I subtract, I'm going to rewrite this up here to have a little bit more room. If I subtract that 17 from both sides, I get 0 equals b. So my y-intercept is b. Now, to finish in y equals mx plus b form, we want to keep our y equals our slope of 17 times x plus 0, or just simply y equals 17x. Now, I can use this equation to find how many trees could be saved if 500 tons of paper are recycled. So our tons of paper are in for x. So y is going to equal 17x for our equation. Our tons of paper is 500, and that's going to be substituted in for x. So y, our number of trees is y, equals 17 times 500. And 17 times 500 is 8,500. So how many trees can we save? 8,500 trees. Now, as we look again at what just happened here, we wanted to write an equation for the total number of trees y that can be saved for the number of tons of paper x. Well, we're going to write our equation in y equals mx plus b form. So we need to find our m, and we need to find our b. So to find our slope, we picked 2 points and calculated the slope. Now, to get our y-intercept, we used our slope-intercept form, y equals mx plus b. We picked one of our points, and we picked 117 as our x and our y. We used our calculated slope of 17. We set up our equation and we solved for b. And in this question, b was 0. So we had our equation y equals 17x plus 0, or just y equals 17x. That's the equation of that line. Now, using that equation, we could put in the 500 for x and calculate our 8,500 trees. So we can represent linear equations multiple ways. We can do it in words. Distance traveled is equal to 12 miles per second times the number of seconds. We can do it with an equation. D equals 12 times s, means the same thing as our words. We can represent this equation in a table. 1 second, 12 miles, multiplied by 12. 2 seconds times 12 was 24 miles. 3 was 36, 4 was 48, 5 was 60. We could do this in a graph as well. 1, 12, 2, 24, 3, 36, 4, 48, 5, 60. So we can represent this linear equation in these 4 different ways. Now, let's stop and reflect. A gym charges an annual membership fee of $10, but you must pay $9.50 for each visit. Yikes. What equation could be used to represent this real-world situation? Well, if we're looking for our total cost, let's set that as y. Now, we have our $10 and we have our $9.50. One of these things is going to be multiplied by a variable, x. And if x is going to be equal to each visit, the times you visit, we're going to do $9.50 times the x plus the $10 a year. So $9.50 for each visit, so $9.50 times x, plus the $10 a year. And that's our equation. As we move on to our last example here, Paul earned $7.50 an hour working at a grocery store. Write an equation to find the amount of money Paul earned, M, for any number of hours, H. Well, we're looking for our money earned. So that's going to be M equals, well, he makes $7.50 for each hour. So if he works 1 hour, 750 times 1 is 750. 750 times 2 hours is $15. And that's how we can calculate. Now we want to make a table to find his earnings if he works 5, 6, 7, or 8 hours. Then we'll graph the ordered pairs. So we're taking this from our words to our equation, to our table, and to our graph. All 4 forms that we can represent linear equations with. Now, we're going to have our h, our 7.50 times h, and our m. Now, the independent variable here is our hours, our time. Time just keeps on ticking, ticking, ticking into the future. So our time is our hours, and that's our x. And our total earnings is going to be our y. And of course, that was our m. And we're looking for, in our question, 5 hours, 6 hours, 7 hours, and 8 hours. Now, if I take my $7.50 and multiply it by 5, I'll get my m, which is $37.50. If I take my $7.50 and multiply it by 6 hours, I would earn $45. If I take my $7.50 and multiply it by 7, I would get $52.50. And lastly, if I take my $7.50 and multiply it by 8, I would get $60. So we've gone from our words to our equation to our table, and now we get to graph. Now, this little funky thing here is called a break. It's a break in the graph. That way we can save space. So everything in this break, we have our 10, our 20, and even our 30 before we get to 40, 50, 60, 70. It just kind of holds all of that in there. We have no data points down there, so we're just saving space when we do that. When we go to graph, our time, we're going to go out to 5 hours and up to 3750, which is somewhere around here. And then we have our 6 hours and our $45. Now, each one of these little lines going up is $5 because we have 40 something and 50. Well, what's exactly between 40 and 50 but 45? So when I look to graph 645, I can graph it at 6 and 45 is right there. How about 7 and $52.50? That's going to be somewhere around there. And then 8, $60 is exactly there. And that's the graph. So once again, we've gone from words to an equation, to a table, and to a graph. That's it. Good luck.